Introduction. Today, Rohan and Aryan are sitting in a cafeteria and enjoying some stuff. Aryan, may I ask you something? Yeah, sure. When you open the cap of the bottle, the bubbles are coming out continuously. Why? Okay, I will tell you. When the bottle is closed, the gas in the bottle is under pressure and remains dissolved. But when the bottle is opened, the pressure is removed and the dissolved gas leaves the liquid rapidly in the form of bubbles. This is an example of Henry's law of solubility of a gas. Okay, now I get the point. But I want to know something more about this. Rohan, to know more, you have to explore about the solutions. Students, you must be curious to know more about this. Today, we will discuss more about the solutions. Objectives. At the end of this lesson, you will be able to define solutions, explain components of binary solution, know about types of solutions, express concentration of solutions, calculate normality, molarity, and molality, calculate mole fraction, understand solubility, analyze solid-liquid solutions, analyze gas-liquid solutions, define Henry's law, know about applications of Henry's law. Definition. A solution is a homogeneous mixture of two or more pure substances, whose composition may be altered within certain limits. The solution may be homogeneous in nature, but it retains the properties of its constituents. The substances which make up the solution are generally called its components. The solution of two components is referred to as binary solution. Components of binary solution. The two components of the solution are solvent and solute. Solvent. It is that component of the solution which is present in a relatively large proportion in the solution and whose physical state is same as that of the resulting solution. Solute. It is the second component of a binary solution, which is present in relatively small proportion. Types of solutions. In a binary solution, components can be either solid, liquid, or gas. There are three types of solutions: gaseous solutions, liquid solutions, and solid solutions. In gaseous solutions, gas is the solvent. They are categorized as follows: solid in gas, for example, camphor vapor in nitrogen gas. Liquid in gas, for example, water vapors in air. Gas in gas, for example, mixture of gases or air. In liquid solutions, liquid is the solvent. They are categorized as follows: solid in liquid, for example, salt in water or sucrose in water. Liquid in liquid, for example, mixture of miscible liquids. Gas in liquid, for example, aerated drinks. In solid solutions, solid is the solvent. They are categorized as follows: solid in solid, for example, alloys. Liquid in solid, for example, mercury in zinc. Gas in solid, for example, adsorption of gases on metals. Expressing concentration of solutions. The concentration of a solution refers to the amount of solute present in the given quantity of solution or solvent. Mass percentage. It is defined as the number of parts by mass of solute per 100 parts by mass of solution. If Wb be the mass of solute B and Wa be the mass of solvent A, then mass percentage of B is equal to Wb upon bracket Wa plus Wb bracket close multiplied by 100. Volume percentage. It is defined as the number of parts by volume of solute per 100 parts by volume of solution. If Va and Vb be the volumes of component A and B, then volume percentage of B is equal to Vb upon bracket Va plus Vb bracket close multiplied by 100. Normality. Normality. It is defined as the number of gram equivalents of the solute present in 1 liter of the solution or milli-equivalents of solute present in 1 milliliter of solution. It is represented by N. Mathematically, normality is represented by N is equal to Wb in grams divided by product of gram equivalent mass of B and volume of solution in liter. A solution having normality equal to 1 is called a normal solution. Molarity and molality. Molarity. It is defined as the number of gram mole of the solute present in 1 liter of solution or millimole of solute present in 1 ml of solution. It is represented by M. Mathematically, molarity is represented by M is equal to Wb in grams divided by product of gram mole mass of B and volume of solution in liter. A solution having molarity 1 is called molar solution. Molality. It is defined as the number of gram mole of the solute present in 1000 gram of the solvent. It is represented by small m. Mathematically, molality is represented by small m is equal to Wb in grams divided by product of gram mole mass of B and Wa in kilogram. A solution containing 1 mole of solute per 1000 gram of solvent has molality equal to 1 and is called a molar solution. Mole fraction. Mole fraction is defined as the ratio of number of moles of one component to the total number of moles of all the components present in the solution. It is denoted by X. Let us consider a solution that contains the components A and B, WAG of A and WBG of B are present in it. Number of moles of A is given by Wa upon Ma. Number of moles of B is given by Wb upon Mb. Total number of moles of A and B is equal to Na plus Nb. Mole fraction of A is given by Na divided by Na plus Nb. Mole fraction of B is given by Nb divided by Na plus Nb. By adding mole fraction of A and B, we get Xa plus Xb is equal to 1. It implies that the sum of mole fractions of all the components in a solution is always unity. Example on mole fraction. Let's take an example of mole fraction. 1 deciliter solution of NaOH contains 4 gram NaOH. Calculate mole fraction of NaOH in the solution. Let's see the solution. We know that 1 deciliter solution is equal to 100 cubic centimeter of solution. Mass of 100 cubic centimeter of solution is equal to 100 into 1.0398, which is equal to 103.8 grams. Mass of NaOH is equal to 4 gram. Mass of solvent, which is water, is equal to 103.8 minus 4, which is equal to 99.8 grams. Number of moles of NaOH, bracket N2, is equal to 4 upon 40, which is 0.10. Number of moles of water N1 is equal to 99.8 divided by 18, which is equal to 5.54. Mole fraction of NaOH, N2, is equal to N2 upon N1 plus N2 whole, which is equal to 0.018. Hence, mole fraction of NaOH in the solution is 0.018. Formality and parts per million. Formality. It is defined as the number of gram formula masses of the ionic solute present in 1 liter of the solution. It is represented by F. Mathematically, formality is represented by F is equal to WB in grams divided by product of gram formal mass of B and volume of solution in liter. A solution containing 1 gram formula mass of solute per liter of the solution has formality equal to 1 and is called formal solution. Parts per million. It is defined as the number of parts by mass of solute per million parts by mass of the solution. It is abbreviated as ppm. Mathematically, ppm is represented by ppm is equal to WB divided by WA plus WB into 10 raised to the power 6. Solubility. Solubility of a substance is its maximum amount that can be dissolved in a specific amount of solvent. It depends upon the nature of solute and solvent, as well as temperature and pressure. The extent of the solubility of a substance in a specific solvent is measured as the saturation concentration, where adding more solute does not increase the concentration of the solution. We consider the effect of these factors in solution of a solid or a gas in a liquid. Solid-liquid solutions. A small amount of solute is dissolved in a large quantity of solvent. Dilute solution. If the amount of solvent is large excess as compared to the solute, the solution is referred to as a dilute solution. Saturated solution. A solution is said to be saturated if it holds the maximum amount of the solute at a given temperature in a given quantity of the solution. Solubility. It is defined as the maximum amount of solute that can be dissolved in a 100-gram solvent at a given specified temperature. The solubility of solid into liquid depends upon the nature of solute, nature of solvent, and temperature. Causes of solubility of solid in a liquid. Many types of forces of attraction are operated when a solute is mixed with a solvent. Inter-ionic attraction in the solute molecules. Ions are held together in the lattice due to electrostatic forces. Due to these forces, molecules are stabilized and the energy released is called lattice energy. Intermolecular attraction between solvent molecules. Water is a polar solvent because of the electronegativity difference between hydrogen and oxygen atoms, constituting water molecule. A dipole is thus created, giving rise to dipole-dipole attraction between water molecules. Effects of hydration energy and temperature. Hydration energy. It is defined as the energy which represents forces of attraction between solute and solvent molecules. If hydration energy is greater than lattice energy, then solution is easily formed. Temperature. Saturated solution represents equilibrium between undissolved solute and dissolved solute. If delta H of solution is negative, then the dissolution is exothermic. In this case, as the temperature increases, solubility decreases. If delta H of solution is positive, then the dissolution is endothermic. In this case, as the temperature increases, solubility increases. Gas-liquid solutions. Gases are generally soluble in water and in other solvents to a limited extent. Solubility of gas in liquid solutions depends on the following factors. Nature of gas. Easily liquefiable gases are generally more soluble in common solvents. Nature of liquid. Those gases which easily form ions in solution are more soluble in water than in other solvents. Temperature. With rise in temperature, the solubility generally decreases because gas is expelled, but some gases find their solubility increased at a higher temperature. Pressure. Pressure is an important factor affecting the solubility of gas in liquids. This is governed by Henry's law. Henry's law. Henry's law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas. Henry's law can also be stated as the partial pressure of a gas in vapor phase is proportional to the mole fraction of the gas in the solution. P is equal to kHx, where kH is the Henry's law constant and x is the mole fraction of the gas. Limitations. The pressure of the gas is not too high and temperature is not too low. The gas should not undergo any chemical change. The gas should not undergo association or dissociation in the solution. Applications of Henry's law. To increase the solubility of CO2 in soda water and soft drinks, the bottle is sealed under high pressure. The tanks used by scuba divers are filled with air diluted with helium to avoid the toxic effects of high concentration of nitrogen in the blood. At high altitudes, low blood oxygen causes climbers to become weak and make them unable to think clearly. Did you know? If a saturated solution is heated, the liquid expands, making room for more solute to dissolve. If a saturated solution cools or is left to evaporate, there is less room for solute, so the solute is precipitated. Precipitated solute molecules often link together to form solid crystals. Tap water is rarely pure water. It usually contains invisible traces of other substances. This makes water a solution. Summary. Let us summarize what we have learnt. A solution is a homogeneous mixture of two or more pure substances whose composition may be altered within certain limits. The concentration of a solution is the amount of solute present in the given quantity of solution or solvent. Normality is defined as the number of gram equivalents of the solute present in 1 liter of solution. Mole fraction is the ratio of number of moles of one component to the total number of moles of all the components present in the solution. Solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent. If the amount of solvent is large excess as compared to the solute, the solution is known as a dilute solution. Gases which easily form ions in solution are more soluble in water than in other solvents. Henry's law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas.